You'll see that midterm 1 exam grade is posted. If you look and it's not there, that means that something is going wrong. If you look and you think that there's something there worth discussing, I have an office hour. If you'd just like to have your midterm a day early, I can hand it back to you if you just go up to my office with me at the end of class. No, not at the end of class. I have another class after this class. An hour after this class. So 3 o'clock. That's my office hours. The other thing, I know eavesdropping is a bad habit, but I think there are 2 questions I want to address. So the first, to get extra credit points, indeed, you just have to come up and talk to me and present the extra credit. That can be during office hour if you want. The other thing I want to point out, so I haven't accounted for that partial points back document that's on Canvas. I have not accounted for that. The way that I will account for it is if you got 90% or above on your in-person quiz, then the on-Canvas thing won't have any effect. If you did better in person than you did in the on-Canvas thing, then the on-Canvas thing will have no effect. So it cannot possibly bring your grade down. Otherwise, I'll take the average between your in-person and your Canvas score to a maximum of 90%. That makes sense? Cool. And sorry, that's sufficiently complicated that it will require me to do things manually by hand with grade entry, which I will make a mistake at some point. So when I do that, check that I've done yours correctly. Nice. So yeah. Yeah. Anyone else need a note packet on exponential and logarithmic functions? Cool. So let's begin. So I think it's reasonable to start with an example regarding the trouble with triples. So let's suppose that you're aboard a Star Trek, and at some point someone brings aboard a single triple, a small cute toy creature. Triples have an interesting property that they split into 2 every hour on the hour. So if you start with one single triple at time 0, then in 1 hour, that one triple will have split into 2 triples. After another hour, those 2 triples will each have split. You will now have 4 triples. In another hour, those 4 triples will have split, and you'll have 8, 16, 32, 64, 128, 256 at 8 hours. So let's just look for a general idea. So from 1 to 2, you multiply by 2. To get to 2, you multiply by 2 again, so you multiply by 2 twice. If you want to just write down how many triples there are after n hours, what thing are you talking about? So it just doubles every hour. So it's just 2 times 2 times 2 that many times? Yeah. There are a total of n 2s. Yeah.
Do you have a sheet packet?
Yes. Absolutely.
Thank you.
And of course, there's a name for this. What is the name for what you get when you take 2 and multiply it by itself n times?
Exponent?
Yeah. You put an n in the exponent. It's 2 to the n. So if you wanted to write down how many triples there will be in 2 days and 1 hour, so 49 hours, that would be 2 times 2 times. I'm obviously not going to write 49 2s in a row. But it's perfectly reasonable to write 2 to the power of 49. And let's go ahead and see just how big that is. Oh, yeah, sorry about that. I zoomed in to make it nice and close, but then, I have to remember to scroll quite a bit. So, obviously I'm also not going to multiply 2 by itself that many times by hand. So 2 to the power 49. Well, it's in scientific notation. We haven't seen that yet, I don't think. But let's just talk about how to read that. I'm not saying you don't already. So that's labeled as 5.63. I'll round it off there. And a computer will write that as E14. And let me just say what that means in a few different ways. That's 5.63 times 10 to the 14th power. And if you wanted to write that out in terms of the digits, well, let's see, it's times 10 to the 14th, so that means I need to have 14 digits after that one, so that's and one more. I may have miscounted. All right, so what's the point I'm trying to get across here? It's big. In 49 hours, so just over 2 days, you will have a significant number of triples. Cool. So that's the function we're going to start studying today. It's relevant for things like population growth, even for population growth in actual populations and not this made-up example from Star Trek. So let's start talking about properties of this function. So for positive numbers, let's just say what exponential functions even mean. We know what it means for positive numbers, right? If I tell you b to the fifth, that means b times b times b times b times b 5 times. Let's just write that down. B to the power n is b times dot 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 times b n times. What if I have a negative power of b? What does b to the power negative 1 mean? Okay, I'll say what it means. So the opposite of multiplying is divided. So the opposite of multiplying by a number n times should be dividing by that number n times. There's what b to the n means. B to the negative n is 1 over b times dot 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 times 1 over b n times. Or if you prefer, that's obviously the same as 1 over b times b times b times b n times. So a negative exponent just means that you have really a positive exponent, it's just in the denominator. The 0 power, what should b to the power 0 be? People have any opinions about that? Yeah.
Do 1.
I think 1. And maybe I'll even try to tell you why it should be 1. So to go from 1 power of b to the next, you multiply by b. So you know what b to the 1 is. That equation should be true. If I take b to the 0, I multiply by 1 more b, I should get b to the first power. But I know what b to the first power is. B. What's the solution to this equation? What does b to the 0 have to be? 1. That's why b to the 0 is defined to be 1. Cool. People happy so far? So that's what exponentials mean for at least natural numbers. And that's most of the exponential calculation that we'll do by hand. But it's still pretty clear that there's something lacking here. You need to have some way of making sense of what 2 to the power pi is. So that's what we'll describe really briefly right now. So first we'll describe what b to a rational number means. So if you have any b to the power p over q, let's try to figure out what that means. And let's do it by first thinking about what 2 to the 1/3 should mean. And so let's think of it this way, maybe. So if I took 2 to the 1/3 and cubed it, that would be 2 to the 1/3 times 2 to the 1/3 times 2 to the 1/3. So that's like that many powers of 2, that many powers of 2, that many powers of 2. And what's 2 to the 1? It's just 2 again? Nice. So I want to know what 2 to the power 1/3 is. It's a number that when I cube it, I get 2 back. So it's a number that when I cube it, I get 2 back. You already know a solution to this equation. What is the solution to this equation? What is star? Or rather, you have a name for the solution. What undoes cubing? Cuboids? Yeah. So 2 to the power 1/3 should mean the cube root of 2. And that's what any over q power means. If you want to describe what b to the p over q means, that'll mean b to the p, and then take the qth root. Or if you prefer, take b, take the qth root, and then raise it to the p power. They're both the same. How do people feel? So in general, that's not something that will come up in many computations by hand. Oftentimes, as soon as a complicated exponent shows up, chances are decent that you're going to wind up getting a decimal approximation using a machine. But it's good to know what this even means. Finally, if you want to, I took this out. No, I didn't. Okay. So let's use those facts to just compute some things. So 2 cubed, let's start by computing that. So 2 cubed should mean 2 times 2 times 2, a total of 3 times. 3 isn't so big, I can actually write that down. If you go and multiply that out, what do you get?
8.
8, awesome. 2 cubed, 8. In fact, how many people just have the first couple of powers of 2 internalized because they come up with some frequency? Yeah. I mean, I guess maybe up to 2 to the 10th is 1020. Oh, shoot, 24. 1024, right? 1024? Yeah. I guess I don't. They come up frequently enough. What about 4 to the negative 3? What should that mean?
Would it be 1/4 times
1/4 times 1/4 times 1/4. Yeah. And maybe we'll take that and we'll just simplify it a little bit. So a quarter of a quarter is 1/16. And then another quarter of that is 1/64. Nice. 8 to the power of 5 divided by 3. So let's do this way. Let's see. So that means I need to take 8. I need to take its cube root. And then I need to raise that to the power of 5. And maybe we can evaluate that without a resolving machine. Maybe not. I guess it depends on whether or not that's a cube root, you know. What's the cube root of 8? Two? Cool. So that's just 2 to the power of 5. So I can look at this and say that is just 2 to the power of 5. And let's see, 2 times 2 is 4, there's another 4, so all of this together is 16, times another 2 is 32. That was fast, but fair enough? People happy enough? All right, and finally, let's try to understand 10 to the power 3 over 5. Let's see, is 10 a number whose fifth root you know? Can you just think of a number which when you raise it to the power 5 you get 10? No. So I'm not going to be able to do the same thing here. So I think here, best we could maybe do is that's the same thing as 10 cubed. Then take a fifth root. And then, of course, if you actually want to know what this is about, you would do it onto a machine. So let's do that. Ten raised to the power 5/3. Somewhere around 46. People feel good right now? Things making sense? Nice. So, the last thing that I want to say something about is what that should mean. So the square root of 2, that has a decimal approximation, right? It's 1.44 and some change. So if you wanted to know what that should mean, well, what it means is take a really big decimal approximation for whatever the thing in the exponent is. That's now a rational number. We have a definition for what rational exponents mean. So that means that I'm trying to avoid saying the word limit, but I'm going to say the word limit. The limit as you take rational numbers that are very close to the square root of 2 and raise that to the exponent. That's the definition of what e to the square root of 2. In practice, though, if you wanted a decimal approximation, what would you do? Just ask your computer, right? And a computer isn't going to use the techniques we've talked about so far to compute these. The computer will use a slightly faster method that comes from differential calculus. So let's, as long as we're doing that, Euler's number e raised to the square root of 2. Somewhere around 4.11. Nice. Any questions so far? Yeah.
I don't know if I'm doing something wrong, but I'm getting different numbers on my calculator.
Nice.
I did 10 to the 3/5, like the one above, and I got 3.98. That's what I got.
Cool. So let's see if I had something wrong.
I think you did 5/3.
Oh, okay, yeah, fair enough. Thank you. Maybe I will point out an easy mistake to make when you're entering something like that. Do you think those parentheses are important? Probably. Let's just check that they're important by seeing what happens if you don't have those. Something different. So order of operation says first you do parentheses, then you do exponents. So if you need to do exponents before division, if you need to do division before exponentiation, you need parentheses. Nice. So the next thing that I want to develop is what do graphs of exponential functions look like? And so we'll sketch a plot by just plotting integer points, and then see if that agrees with the computer generated graph. So let's compute the powers of 2 and plot them. 2 to the 0. So I guess that point should be on the graph, 0, 1. 2 to the 1. Nice. Let's just keep on going. 2 to the 2 is 4. 2 to the 3 is 8. 4, 5, 6, 7, 8. 2 to the 4 is 16. 8, 9, 10, 11, 12, 13, 14, 15, 16. And now let's go the other way. What's 2 to the negative? Well, yeah, 2 to the negative 1. Yep. Right, that should be 1 over 2 to the 1. That's 1/2. Right, you should think of negative exponents as meaning divide by 2 that many times. So 2 to the negative 1 is 1/2. 2 to the negative 2? What's half of a half? 1/4. which I guess if you like decimal approximations, you can write that as 0.25. 2 to the negative 3 should be half of that. What's half of a quarter? 1/8. And finally, 2 to the negative 4 is 1 over 16. And I think at the scale I'm able to draw, I can't differentiate between 1/16 and 0, basically. So here's what the graph seems to be looking like. I'm going to get an idea of what the graph maybe looks like when you plug in all the numbers by like shading in between. So doing that, we'll see a graph that looks something like this. And maybe in order to get an idea if that's actually reasonable, I'll make it so that the picture stays up. There's the graph of 2 to the x. Does that about agree with what we just did by hand? Yeah. So that's what the graph of 2 to the x looks like. Do you think other exponentials will probably look pretty similar? Yeah, probably. Hold on to that idea at the end. Though maybe I'll spoil it a little bit by saying there's 1/2 to the x. Does that look the same? Yeah, it looks kind of the same. We'll come back to that. All right, so exponentiation and algebra. So there's some algebraic laws that exponentials satisfy, and let's just try to build them. And let's build them by writing them down in some basic cases. So let's figure out what 2 to the 5 times 2 to the 3 is by first writing it down. What does 2 to the 5 mean? Not like, is it probably 2? What does it mean?
2 times 2 times 6.
Yeah, it's 5 2s in a row with a little dot between each one. So there's 2 to the 5. What does 2 to the power 3 mean?
3 times.
Do those parentheses matter? No, multiplication is associative, which means the parentheses between just multiplication don't matter. So how many 2's are there in a row right there? 8. So that's 2 to the 8, which maybe suggestively I'll also label as 2 to the 5 plus 3. What do you think? Does that same rule, do you think that'll work in general? Yeah, of course, for the exact same reason. For any 2 exponentials with the same base, you'll notice I'm specifying that the base has to be positive. There's a good reason for that. B to the x times b to the y is b to the x plus y. Cool. That seem pretty okay? All right, so let's use that to do something. Let's compute, without access to a machine, 3 to the 3 halves times 3 to the 5 halves by using this string. So, well, everyone seems to be walking, so maybe I'll even just like stall for a moment. You'll tell me what it is. I think that's more useful. What are people getting?
You have 3 to the 8 halves, and then you can simplify 3 to the 4.
3 to the 4? Which, that's a number that we can figure out what that is, too. So maybe I should pause. Are people happy up to there? Do people want me to write anything more? Okay, cool. So it's 3 times 3 times 3 times 3. What's 3 times 3? 9. So that's 9 times 9. Oh, hey, that's a number that you just know, right? It's 81. Cool. So what's the payoff? I don't know how to compute 2 to the 3 halves by hand. Right? To do it, I would need to know the square root of 2, or the square root of 27, neither of which I know. But when I multiply it by 3 to the 5 halves, it becomes something that I do just know what it is. It's that. So these exponential laws can let you simplify things in some cases to places where you don't need a machine to help you do any computation. Here's the next exponential law I want to get. 2 to the 5 to the power 3. So first let's deal with what that power 3 means. That means I should take whatever's in the parentheses and just write it 3 times next to itself. So I'm going to be maybe excessive with the color coding. 2 to the 5 times 2 to the 5 times 2 to the 5, parentheses, parentheses, parentheses. All right, and maybe this is an excessive thing to do, but do you know what 2 to the 5 means? Yeah, it's take 2, write it down next to itself 5 times. So let's do that for each of those pink 2 to the 5s. So, parentheses, 2 times 2 times 2 times 2 times 2, 2 times 2 times 2 times 2 times 2. I think I counted correctly each time. Regardless, how many 2's are there now next to itself?
15.
15. 3 times 5 of them. Was there anything special about these numbers that made that work? No, this is a general rule. If you have any 2 bases, any single base, and you exponentiate twice with that same base, you multiply the exponent. B to the x to the y is b to the x times y. So let's use that to get another computation. Let's make this go away. Three to the 9 halves to the 2 thirds. Let's try to compute that. So I see an exponential of an exponential. So that means I can just multiply the things and the exponents together. Let's do that. So that is 3 to the 9 over 2 multiplied by 2 over 3. And for emphasis, all of that stuff is now in a single exponent. See anything that simplifies or cancels or something? Yeah, what do you see?
The 2's.
2's.
And the 3 and the 9.
Yeah, cool. Divide by 2, multiply by 2, undo each other. 9 divided by 3 is 3. So that just becomes 3 to the 3. So I guess that's 27. Ooh. So let's use this idea again, paired with something that we just absorbed in the computation we just did, to compute 27 to the power 2 over 30. So first of all, by looking at the computation we just made, is 27 a power of something? Yeah, what is 27 as a power?
3 to the 3rd.
3 to the 3. Oh, this line. So let's use that. 27 to the power 2 thirds is 3 to the power 3 raised to the 2 over 3. Cool. Is that a thing that you know? Or can walk out? Yeah, what'd you get?
Nine.
I think it's 9. Does that agree? Nice. Let's also use this idea to solve an equation. Let's try to solve the equation 4 to the power x equals 42. And here's the strategy I will suggest. 4 and 42, they have something in common, right? They both have 2's in common. So let's try to write things in terms of powers of 2 and use that. What's 4 as a power of 2?
2 squared.
2 squared. 4 is 2 times 2. So let's rewrite this as 2 to the 2 equals, what is 32 as a power of 2?
2 to the 5th.
2 to the 5th. Oh, and I lost the x. Goodness. 2 to the 2 to the x equals 2 to the 5th. Alright, so let's mess around with this a little bit more. Here I see an exponential of an exponential. So the left-hand side, how could you rewrite it? So
2 to the 2x.
yeah, right? You see an exponential and then another exponential after that. The things in the exponent now multiply. So 2 to the 2x equals 2 to the 5th. So that means 2x needs to be a number, which when you raise it to the power 2 gives you the same output as 2 to the 5th does. Let's go ahead and look at this graph. By looking at that pink graph, 1 to 1 or not 1 to 1? 1 to 1. So the only way two different things in the exponent above a 2 are the same is if the 2 to the this equals 2 to the that. So, do I see a situation there that I can now simplify in the equation I was actually walking in? So how can you rewrite 2 to the 2x equals 2 to the 5th?
2x equals 5.
2x equals 5. All right, so what's x? 5 halves. So you can use these tricks to solve some equations. No, that's all. Let's take a look at this next equation. 9 to the x equals 27. Maybe it looks like everyone is walking diligently, so maybe I'll pause for a moment. They'll tell me what x is. Cool. What have people got?
3 halves.
I got 3 halves. Anyone want me to talk about it? All right, we got a 3 halves. X equals 3 over 2. Here's another equation. 5 to the x equals 7. Could we do the same trick with that equation to solve it? Well, not in any obvious way. 5 isn't a power of anything other than 5. 7 isn't a power of anything other than 7. So we need some sort of other trick. We will get another trick in the form of logarithmic functions next time. So we will be able to solve that equation tomorrow. And maybe I'll even tell you, essentially we're going to make up a name for this solution. We will call it the log base 5 of 7. But we'll talk about that in more detail next time. So the last thing I want to do is I want to get general graphs of exponential functions for an arbitrary base. So far we've already done 2 to the x. And its graph, I guess, looks something like this, though I should be more careful to go through the points that I've labeled. Something like that. So let's think about this next. So we've talked about what a negative number in the exponent means. It means you divide by that number that many times. So 2 to the negative x, that's the same as 1/2 to the power of x. Oh, nice, but That means I take the graph of 2 to the x, and I put a negative sign in front of the x. What does that do to the graph? Yeah, it does this. It reflects it over the y-axis. And if you're not very careful, then you might mean the right thing, but you'll say it reflects it over the x-axis, which is not correct. So there's the graph of 1/2 to the power x. And there's one exponential that behaves weird. Let's think about powers of 1. What's 1 to the power of 0? 1. Anything to the power of 0. What's 1 to the power of 1? What's 1 squared? 1 cubed? What's any power of 1? So what does the graph of 1 to the x look like? A straight line at y equals 1. Yeah. So I'm going to copy that down here also, though there's no hash marks anymore. Yeah. So far I haven't done much. I've just copied down 1 to the x. Let's now just think more generically. What does the graph of any exponential look like? And we'll do it by plugging in some points. So pick some number b that is bigger than 1. Maybe it's 2, maybe it's 7, maybe it's 1.05, whatever. Those will affect the scale, but I don't have any hash marks logically, so I don't have any scale to get wrong. What's b to the power 0? To the power 0? 1. That's an easy mistake to make. So, that means I definitely go through the point 0, 1. What's b to the power 1? b. And I guess the only thing I can tell right now is, should I draw this dot so it's above 1 or below 1? Above, because b is bigger than 1. Maybe it's that big. At 2, I'll see b squared. Oh, gosh. One comma b, 2 comma b squared, and so on. The other direction I'll wind up dividing by b. On the other hand, if b is less than 1, but still positive, the graph of b to the x will look pretty similar, but the other way. So maybe I'll draw the picture and then try to justify it. So, even if b is less than 1, what's b to the power 0? 1. Any reasonable thing to the power 0 should be 1. You get yourself into trouble if you start trying to figure out what 0 to the power 0 should mean. So we just won't talk about 0 to the power 0. It's an illegal thing to talk about. Similarly, you'll notice that I'm only putting positive numbers in the bases of exponents. That's because if I don't, then when I have to figure out what negative 2 to the 1/2 is, I need to compute the square root of negative 2, which is complex, which means that I can't graph it at the minimum. And you get into even more trouble if you try to compute negative 2 to the power of pi. Then it really is hard to make sense of. So we just won't. All of our exponents will have positive bases. Alright, but let's say b is like a third. If I start erasing one third of powers, that means I multiply by one more times. Does that get smaller if I do it more times? Nice. And going the other way, I need to divide by a third a bunch of times. That's the same as multiplying by 3. Yeah, that is. So I think we that's correct. Neat. Any questions or comments so far? Movies. Let's point some things out about these graphs. Now, I guess before even going to these questions below, looking at these graphs, what are some observations you can make by looking at these graphs? There are lots of correct answers.
can see the domain.
You can see the domain. Yeah, great. Let's do that. What are the domains of these functions? Yeah. But the domain is what x values do you see? And it keeps on going this way. It gets like really far up, but you can plug in very big numbers into exponents. Range. What's the range of that Faust function? Let's try to say what's not in the range. Are negative numbers in the range? No. Looks like I never get to be negative. I multiply by dividing by a number a bunch of times. Can I ever get to 0? No, I'll get really close to 0, but I won't quite make it there.
So 1 to infinity?
I think it's 0 to infinity. Because I have to get, these things are less than 1. They're getting close to 0. Oh, and I guess I was just pointing to this graph. Does that graph indicate the same range? Yeah, the solutions to equations will be like on the opposite side of the y-axis, but that's okay. How about this function? What's the range of that function? What outputs does it achieve? Does it have?
Outputs are all 1.
The outputs are all 1. So what's the only thing in the range? 1. So I would say this as when b equals 1, the range is the set containing only 1. Maybe before that, going on to the next item, maybe I'll ask this question. Even or odd? Even? Odd? Neither? Yeah, of course, it's neither. Same question? Right, same answer. Neither even nor odd. Where is this function increasing? Is it ever not increasing? I think this is always increasing. What about the second one? I should make clear what I mean by the second one. This function, increasing or decreasing? The opposite. I guess this is, depending on how you interpret increasing or decreasing, it's either both or neither. If you always stay the same, then probably you would want to call that neither increasing nor decreasing. Depending on the mathematician you talk to, they would want to say, well, I'll just count it as both. So maybe I won't write anything there. Do these functions have any horizontal asymptotes? Is there a straight line, a horizontal line that they get close to? What horizontal line are you thinking of? 0. They're like different from the horizontal asymptotes that rational functions have, though. Rational functions like do the same thing to the far left and the far right. Here we have very different behavior on the for positive and negative numbers. Oh, so that's how they differ from rational functions. Maybe I'll just like do a quick, what do you think the definition of this question? Would you say that this function has a horizontal asymptote? Does it get close to any straight line? Many people would want to say yes. Many people would want to say no. Somehow it is that straight line. But it is really close to itself. I would want to say it does have a horizontal asymptote at y equals 1, but I get that that's a weird edge case. Neat. So, I think that's what I want to talk about today. As a reminder, so maybe like sales pitch. There is an extra credit right after this. There are a great many extra credits that will start coming in now. Exam grade has been posted. Go ahead and check yours. If you want to have your exam a day early, because I don't have them in hand back yet, I'll have them for you tomorrow, or I have an office hour in an hour. Do I? I do, right? I do have an office hour in an hour. That's the wrong class. Yeah, Thursday from 3 to 4. Is today Thursday? Today is Thursday, right? Okay. Yeah. Okay, cool.
Have a good day.
Yeah, you too.
I don't know yet.
Yeah. Let me turn off the recording first.